So, good afternoon, everyone. I'm Akash and she is Arushi. We will be presenting three papers today. One is on tokenization and the other two are on the data mixing. So, I will be presenting the tokenization first. Yep. So, I will be presenting the downstream task-oriented neural tokenization as post-processing with vocabulary restriction. So this paper mostly addresses a critical challenge to solve this problem, the optimization tokenization of a already trained model without even modifying them. So there are some previous approaches. One is joint training, where we train the tokenizer and the model together. And then there is unigram-based tokenizers, which are really computational expensive. And then there is one more Optok. Optok was one of the first approaches which optimize the tokenization as post processing, which this paper also does. Yep, can you move next? So before going next, let's understand why tokenization even matter. So see here, if you take a word unhappiness, there can be different tokenizations for that word, right? Each tokenization here gives different context to the model, and the model will behave accordingly. Same like in interesting movie, if you keep different tokenization, the different result will come from the model. So this will especially matter for the languages like where we do not have white spaces like Chinese and Japanese. So again, the goal is to find the optimal tokenization, the best tokenization out of all these. Yeah. So the paper suggests a two-step approach. So firstly, what we do is we collect the optimal tokenizations by evaluating each tokenization through the downstream model, the existing downstream model, and then we collect all those tokenizations, create a new data set, and then train a new neural tokenizer based on that data, so that we can use it later to understand the patterns in tokenization. So let's deep dive into the detail of these steps. So the first step is collecting the optimal tokenizations. So what we do is we generate n different tokenizations for a text sample in the dataset. Here you can see interesting movie. This is the loss for generated by the existing model. So here you can see the minimum loss is in this tokenization. So we'll take this tokenization and create a new data set of it. And yeah, so this in this paper we have used three different tokenization methods. One is Unigram, then there is byte pair, and then backslash. So we create n different for all these.
So when you say the loss is, I mean, what architecture, what model, what task? Is it just task for the mass language modeling loss?
So it's a downstream task of text classification.
Not really text, not really mass language modeling loss. So classification it can be very different from text generation.
Yeah.
So this is maybe they're trying to make it efficient and therefore the classification is pressure. Just because see, right? We just try to do classification is supposed to be very restricted. pre-training.
So the paper didn't use any other downstream. They just used text classification only there, and they didn't give the results of.
One text classification kind of task or multiple? Because you have presented only one loss. If it's multiple, you should have a vector of losses. Are these really losses of the classification, or are they losses of the mass language modeling? I mean, if it's classification, why should which are loss?
No. These losses are of the model, model classification, but the whole process is.
Which loss? Mass language modeling loss. Which loss? Loss of the model means a pre-training model, right?
Yes.
You only assume, I hope this is the mass language modeling loss. Right? That. Okay, so we are not going to go back to classification.
No.
But you said the downstream loss, what is used to measure the loss? No. Loss is nothing to do with downstream.
Yeah.
Yes.
Yes.
Yes or no? Is a loss, does a loss have anything to do with the downstream?
No.
Okay. It's just the, okay, go ahead.
Yep.
I mean, loss seems to be even less representative than perplexity. If I'm actually looking at the language modeling task, you look at perplexity because loss requires some discretization. Loss, to get loss, I'll have to say, okay, this is a softmax, I'll discretize and then compute loss.
Yeah.
Whereas if it's perplexity, it's just continuous. Yeah, in the first and the second and the third, all of them will matter in the distribution, right? When you are trying to predict the token, most probable, second most probable, third most probable. Loss and only look at the most probable and discretize. Perplexity looks at the distribution overall. So I'm not very convinced that this is a good thing, or maybe they're not done this. You read clarity about the loss. Why you 100% sure the loss is just a mass language modeling loss? So get clarity on that. That's important. Okay.
So we have collected all the so we are and then we by LSTM based tokenizer to reproduce those patterns for a new text sample which is coming. So they have used this loss function and they have used the famous Viterbi algorithm for the inference. What is this? This is log loss. And then
is it likelihood?
Yes, it's negative.
Likelihood. So negative of likelihood. So you are just producing the token. So you take the best tokenizer as per some downstream tasks not have a role to play here, right?
Yeah.
And
so it depends on the loss. Like if that loss is actually based on the text classification, I don't know about that loss. Then this is only for text classification. Otherwise, it will be in general.
You said you are only measuring the objective, the loss function of them.
I am not really clear about it, but I think that it should be text classification. The downstream
task.
task.
Not. Here, the loss function you written as likelihood loss only. Negative likelihood. Hey, this is an optimization course. This should be the thing.
This is a completely this you can keep the model apart now. This is we are training a new tokenizer model.
That is okay.
Yeah.
The previous there was some loss that was used to minimize, which is not at all clear. That is important. You are saying that doesn't matter. It matters.
Yeah, it matters. Yeah, I know. Yeah.
Now you are saying once you are not clear what loss they use, please get that clarity. Once you do that, then let's take the step. You just for the step two. Step two, you just use the tokenization data, synthetic data, which is basically tokens.
Yes.
Same text.
Yes, but different tokenizations for that. The optimal tokenizations. Yeah. So here the new tokenizer is completely independent from the downstream model. And yeah, you can. So before moving on, there is a problem in this because this new tokenizer can generate unknown tokens which are not in the vocabulary of the existing model. So in that case, it might throw an unknown token error. And for so like they in the paper they have showed for byte tagging they have used byte tagging also tokenizer, and it showed up to 11.5% of unknown tokens. And they wanted to solve this problem by restricting the vocabulary generated by this new tokenizer. Yep, you can. Next.
So how is tokenization was not using a neural model, right? Previous slide. I mean, where was the neural? So you're saying the neural tokenizer was trained to generate tokens? Sorry, I missed it. Where was the neural tokenizer trained?
Step 2. There it is.
So this is training the new tokenizer is completely independent, but you're training. Yes, I just said it. So it's a segmentation. Segment. Okay. Sounds very ambitious. Okay.
So we will check the vocabulary to solve that problem. What they does is they use a vocabulary filtering mechanism. You can go to next vocabulary. Yeah. So they consider all the possible tokens. Let's say these are all the possible tokens generated by the tokenizer. Then we check every token if it is present in the vocabulary or not. We assign probability only to those which are present in the vocabulary and skip all these which are in here gray in color. We assign the probability to 0 so that they are not passed to the model. That will actually solve the unknown token error. So for experimental setup, they have used for Chinese they have used these 3 different data sets, and they have used this for Japanese and Twitter for English. Yep. Previous. So they have compared this method with the original method where we do not change the tokenization, and then the unigram and bytag and opt-out. So here are the results they have shown. So here, as we can see, this is the proposed method. It's highlighted as it's performing very well compared to the other methods. The original one was showing 93, and then the proposed method showed 93.113, and you can compare it with the others also. Here, Optok was also performing well, but it is supported only for unigram method and not the other ones. And at the same time, Optok was computationally very expensive. They used n is equal to 3, and here the proposed method used.
Optok is?
Optok is also a similar method based on unigram tokenizer, and they have used 3 different tokenizations and find the optimal one. But in the proposed method, they have used 100 of it, and for all the 3 methods.
Why is their proposed approach faster than Optok?
Why our proposed method is faster than Optok?
Yeah.
Yeah. So the Optok was fine tuning the older unigram method. They were changing the parameters according to the optimal tokenizations. But we are completely training a new tokenizer here in the proposed method. So you can see the reproducibility results also, and here the unknown token rate, which was 11.5 for bytag, and for the proposed method, it is just 0.1 for rhyme data set, and for the other it's 0. They have used different n values also, and they find n is equal to 100 as the best. If you increase the n the number of the tokenizations, then the score is actually increasing, but at the same time it's computationally expensive also, because we have to do 200 forward passes if we keep n is equal to 200. Yes. So here the perplexity score compared to the older methods, and
Oh, it's higher perplexity.
yes.
You don't understand.
No.
Perplexity should be lower, no? Many more tokens, higher perplexity. What is byte tag? And I'm not understanding what you have written here. Byte tag, many more tokens, higher perplexity. That's the
Higher. Wait.
where? Okay. Go ahead.
So then we have tried figuring out like how this can be used in Hindi language, and this can quite work well in Hindi language, as in some words like Vidyalaya, we can tokenize it as uh, Vidya and Lya in different, and same in Ladkiyon, which in general, let's say if you are using any unigram based tokenization, it will split it. It can split it in like any way. We do not know how will it split. It is just the probabilistic approach. Yep. So, despite of giving good results, there are many limitations to this paper. One is the computational cost for higher data sets. So, the data set they have used now, it has around 537K text samples, which if increased to millions and billions of data samples, then it will actually increase the forward passes, and the computational cost will actually increase. Yeah, that's it, I think.
Can I stand down?
Sure.
It's fine, it's fine. I'll have to show it so in case I have to point. Okay, so now we're talking about data mixing. So what exactly are we trying to do over here? At least from the two papers we have, is when we're training a model. So now that the models that we have, they contain information from a lot of multiple domains. So we don't know for which test we are running, what would be the optimal domain. For example, if you have a potluck, you have a lot of food which comes in. Now, to make an ideal plate for a specific person, you would have different amounts of each food. Similarly, data mixing, you would need different weights of each of these domains. So how do we get an optimum one for that? But now if you want to train a specific data set just for each test we want to do, that would lead to a lot of it would be a lot of computational cost. At the same time, it's very focused only on one thing. So we are trying to find the ideal weights which would help for most testing data that we could have. Okay, next. We have two papers in this. So first I'll start with the first one, which is about Do Re Mi. which is optimizing data mixtures, speed up language model pre-training. Next. Okay. And now, as I said earlier, we often train it on many domains. So we get suboptimal domain mixtures, which leads to reduced performance if and we waste a lot of trying to do over here is get a domain mixture which speeds up the pre-training process, while at the same time we're improving our overall performance of the data domain. Okay. Also, at the same time, previously what the methods were being used were either down training, which is when we already know what we're trying to test, we change our weights accordingly, or using heuristics, manual heuristics to change the weights. So all of these are based on our assumptions of what weights we would need, which can lead to a lot of suboptimal performances. So what we're trying to do is train a model which, based on the data, is able to change the weights accordingly. Okay, which is where DOREMI comes in, which is domain reweighing with minimax optimization. So this is over here, the main concept that is being used is we first have reference domain weights, which are taken from a reference model. Then we take a small proxy model, which is a kind of a subset of the bigger main model we're trying to train. And we train these weights on that model. Based on that, we get the optimized domain weights. And those weights are then used on this large data set to see how it performs. So we don't, it's the only time we train it is over here. And then we use it here, and so it is at least like 30 times bigger, and we are seeing how it performs. Next. Okay, so the whole setup over here is, as I said earlier, we have different domain weights that we begin with. The step one is taking a small reference model where we train a small model for the reference domains, which will be different from for the different data sets. Go back. Setup. Yeah. Yeah. So what happens to that is the computational time that is taken to train it reduces. And we are still, what we see is we get similar results. Actually, it performs better than the baseline things we had started with. And instead, if we trained the 1 billion or 8 billion parameter data set, it would take a lot more cost. So instead, we train it on the smaller proxy model and then use those weights on the bigger model. Need not be. It does not have to be. It can be anything as long as you have the weights. In the end, we are training it on the proxy model. So the proxy model has to be a subset of the main set. Reference models, if you're just getting the reference weights. In the end, we're training it on the proxy model. So it doesn't matter what the reference model was, as long as our proxy model is similar to the large set.
The assumption is that the proxy model is trained on a data set which is a subset of the reference model on which the data was trained.
Or the reference model doesn't train any data. The proxy model is training the data.
We first train a model TF. You've written.
Yes.
So your reference model, you train it on some.
But from that, we're getting the baseline parameters itself, baseline weights, which are then fed again to the proxy model.
So the baseline data is fed to the proxy model? What is fed to the proxy model?
Weights for the different domains is fed to the proxy model. Next. Okay, then now we train the small proxy model using group DRO, where we are trying to, so it's a dual thing. So we're trying to maximize the weights while minimizing the error that we're getting, the log loss error across all of these domains. So this is the reference loss, and this is our loss that we're getting in each training set. We are trying that this is minimized. So you have a doubt?
So reference model is the black box model.
Yeah.
We
We,
train on data set which you don't have
yeah.
access to. And proxy model?
Proxy model, we are training it. And we're
Uh-huh.
trying to see at which case we would get the minimum loss. We'll take it in batches, we'll test it, then we'll get the alpha that exponentially based on what the loss was and keep
Domains
changing
all
it.
belong to the proxy model.
Yes.
There's no notion of domain in the reference model.
But we would need the same domains in the reference model as well to get the
That's
weights.
what the assumption is made that there's similar domain in the reference model.
Yeah, but we can have other domains as well over there. It doesn't matter. We just need the weights of the domains which are being used in the proxy model. Yeah, there has to be some intersection.
Not intersection, there has to be a strictly subset, right?
Okay, it has to be a subset. Yeah. The reference model. Yeah, the proxy model has to be a subset of the reference model in terms of domains. Need not.
That we have for training the proxy
Yeah.
model must be a subset of the
Yeah.
data that was used to train the reference
Yes. Next. Okay, so this is the algorithm which is used over here, where it's taken in batch.
model. But what is it doing? It's still not clear. What is the
What is?
algorithm doing?
So what?
I mean, we can go back to this. So it is taking the reference
Yes.
model as a black box, trying
Yes.
to minimize the max score or the
So from the reference model,
alpha is the weight for the ith domain
yes, in the batch.
in a batch.
Yeah. So what we're trying to do is we run it like iterately. There are 3,000 steps, 30K or 20K steps, depending on the data set you're using. Over here, they use Pile and Glam. So both of them are different iterations, and each time they're just trying to minimize this. So from the reference model, whatever weights we get, now we are training it over here on the proxy model, and the proxy model has to be a subset of the bigger data set we're finally trying to use it on.
So the alpha i's are obtained from the reference model.
The initial one, the initial alpha.
Maximize over the simplex. Alpha is not obtained from the reference model.
Alpha reference, it starts with alpha reference. That is got from here, and then as the steps go on, this alpha will keep changing.
So you're saying that the reference model is only used to
Get the weights.
initialize the weights.
Yeah, initialize the weights. It doesn't use,
Very,
it's not used at all after that.
you just throw it away after initializing. Why is it reference?
I'm not sure how deep it works. They just
You're
do.
wrong. Look at this. In the expression itself, L theta x minus L reference x. So L reference x is not thrown away, it's kept all the time.
Just to, because that is the weight we started with. So we're seeing how much change is there
So
from
the
that.
reference model is preserved.
Yeah,
It's not that reference model is used only to find the data mixing components.
it's used to get the initial weights which we would have used otherwise. These are
But it
the
also
these
continues
are the
remaining
base.
reference model also continues remaining part of this objective.
Yeah, but we're trying to minimize that part itself, right? We're trying to minimize that loss that we're getting, which is where this comes in. This is just so that we get the difference. This is for the entropy change. This is the excess loss. So we're trying to give higher weights to those which have higher excess loss, because that means that they were able to be used well in the reference, but over here they weren't trained well. That means you need higher weights for them here in the bigger model. So that is why the reference is used. And similarly, if we have high entropy domains, but then their L reference would also be low. So your net loss over there would be lower. So then in your final bigger subset model, the 1 billion one, you would have a lower weight for it because anyways it can't perform well. Or the ones which are easier to test, the low entropy ones would anyways have a lower excess loss. So they would have lower weights. We're trying to give maximum weights to those which had difficulty learning in the proxy model. So we are trying to train it on the proxy model. There is a possibility that when we use the proxy model data, we won't get the optimum solution. But we are trying that in the end, when we use the 1 billion wala data set, it works well on that. It's able to account for which domains are the toughest to train. Next. Okay, then when we don't train the large model over here, it says that, but it is more of we're using those now on this and we're seeing how it performs. Like example, how ChatGPT works. When we feed it a question, after that it just has to respond. So that is what we're going to be testing here. How on one approach, how it responds and how much it's matching what it should have answered. Next. Back. एक और The algorithm? So it's grouping it into bands. The minimizing of the first one maximum. In the over here, I don't remember, but it's for the net. If I go previous. Huh. Yeah. So that this is for each step, like batch that we've taken. What? This is the theta. And then we're trying to maximize over here based on what this value was, we're changing the alpha.
No, I'm asking where is the alpha simplex?
Where is the alpha?
Max over the alpha, right?
Yeah, so see, based on lambda over here, we're changing alpha. We're taking maximum of the lambda, so our alpha will become max. It's depending exponentially on the lambda.
Okay.
Now back. Now there is another way to do this, which is iterated Doremi, where the same thing that we did using the proxy model, instead of just using it once, we use it iteratively. So we use the alpha weights we get from one, we again test it, get another weight, and do that a few times until we reach an optimum weight, until we reach optimum weight. So this is using GLAM, but it isn't using Pile, because over there we have, okay, I'll explain that when we come to that part. So now the experimental setup that we have, we use two data sets. So we tested two different data sets, which were Pile and GLAM. Pile has 22 diverse domains, while GLAM just has 8. And in Pile, they have baseline reference weights already defined. So that is what we used. While over here, they started with uniform weights for all domains, because in GLAM dataset, they already have the Oracle or ideal weights defined. So they didn't want to use those. So they used uniform weights for all of them. Now in GLAM, we used iterated Doremi because the number of domains are very less. So even if one of them isn't optimized, we would have a lot of error. So that is why we do it iteratively, while over here we have 22 diverse domains. Even in one Doremi cycle, we are able to get optimum weights. And then the training setup, we have the exact same steps as what is in the baseline as what we use when we are testing the data set. So 200,000 for Pile and 300,000 for GLAM. And each batch size is of 512, and the max token length in each is 1024. Next. So now the results that we've achieved from all of this. Average one-shot downstream accuracy. So here, this is what the baseline was performing when we went from a 280 million, this 280 million parameter data set was a proxy one, and 8 billion was what we were training in the end. As you can see, as we reach the end, the exact matches have increased and the computational time is also less. So for the lesser number of steps, we're able to get better performance. Now, this was Pile and this is GRAM. Now, in GRAM, they have done it iteratively. So they've shown how the performance is there for each iteration. As you can see, the purple one has performed better than either and has actually performed better than the downstream tuned one, which is the Oracle, where we already had the weights predefined. Okay, now this, one major thing is we are reassigning weights. So there would be some domains whose weights get lower. But if you actually see, if you now test it on any one of these domains also, the new weights that you get, you see that each of these, in each of them, the perplexity is actually reduced. Even though the weight that that certain domain had might have reduced, that is because in the end, that domain was easy to learn. So you didn't need that much weights to it. So the model as a whole was able to perform well, even if it was just testing on that specific domain, which is shown here for Pile, which is once again, sorry, back, which is called positive transfer effect. Now, okay, these are all, so there are a few issues that were seen. One was that when they moved from a 280 million data set, which was proxy, to 1 billion, the weights that were assigned were different in the end. In the 280 million one, Pile CC got the highest weight, while when they started with the 1 billion proxy, they saw that OpenWeb X2 got the highest one. So from this, there was an inference that we actually it's a non-convex domain. We could have, based on which model you start with, you can have a different ideal weight. As long as they're all performing well on the final one, it doesn't matter. But based on this, there comes a question that how do you know which proxy domain you should take? How do you decide which is the ideal number, which they also weren't able to figure out, and that is what we were thinking we'll try to do. Uh, um, then these are more results that were done where they did ablations and saw how it performs. Yeah. No, they didn't. They said that it's. But there's no ideal way to do it. Like, you can't guess that this is what you would use for it. So that is what we were trying to discuss with them, how we could go about it, because we have a pile data set which we can use. Shravan. Okay, now another thing that we see is when our main aim is to scale the model. Now, when we scale from a 1 billion proxy model to an 8 billion proxy model, though, the perplexity has increased in comparison to when we had started from a 280 million one to an 8 billion one. While till then, when we had gone up, the perplexity had reduced. So from 70 million to 150 million to 280 million, the perplexity had reduced. It increased when we used 1 billion. So there is an optimal value in between both of these where it would perform, where the perplexity would reduce the most. But we don't know how to test it, and neither did they tell anything. But this was a major influence on that. Then next, then over here, okay, so this is the same thing that I showed just in images. Now, another result that we got, when we're training, which they got, sorry, which is when they performed it, they saw what the weights were at each step. As you can see, initially there is a lot of change, but after 50,000 steps, it's almost stagnant. It's become a plateau where the weights aren't changing as much, even though they went till 20,000 steps. So one other thing that we could do is extrapolate. We could stop at around 50,000 steps, and based on how it has performed till there, figure out what the weights would be for the end and see its performance on the model. So this was for GLAM, this was for this was a pile, this was for GLAM. They didn't. They said you could think about doing it. In extrapolation, you could have different ways you could do it. Linear, train another small meta model to do the same thing. No. Yeah. We just have to speak to him. He told us to present this to him as well. After that, he'll tell us. Okay, this is just a proof for how what I said earlier, that even though we train it just on we change the weights around, all the models perform. It performs, the perplexity reduces for even if you test it on a single model. So they had performed a test where they had different domains, which was non-noisy, non-noisy, intermediate, and noisy. And when they changed the weights for all of them to the optimal ones, each of them still performed well. And then they had a proof for that. Now, as I said, the limitations and future work on the current paper that was there, extrapolation. If we did it at around 50,000 steps, we would save a lot.
Steps as a
large model. Yes.
But I don't know the large model, how many steps it was run, right? That was black box to me.
I think they had that information, that how much it has.
You think they have that information? Because there's nothing, I mean,
I got it.
So far, it was assumed black box, right?
Yeah, but this is testing. Wait. Yeah, it is black box. Okay. Go back.
Or maybe what they mean
is the model. Testing on the bigger model as the steps change. And this is the baseline one. So this is those same weights that we're getting on each step, that using that on the larger model, the bigger one, because they talk about training that also to a degree. But so the weights which are changing here, that are put on the bigger model and seen how it's performing. And similarly, the baseline weights that we had as they're trained. One of the limitations, which was extrapolation, which we are thinking of continuing later on. Then transferability across model scales. This we are not sure how to go about it exactly, so that's not something we're looking into. And then domain. So right now in this particular paper, they use domains based on where it came from, Wikipedia or Twitter or wherever. But instead, that is coarse grained domains. Instead, if you use finer grained domains, such as grouping them based on the topic, we would have better results. Just the big problem over there is DRO pessimism, where you you put, because there are topic domains, a few topics get highlighted a lot because they're very tough to learn. So then you end up putting too much weight on those, and then they don't represent the overall task too well. So now with these things in mind, the second paper comes in, which actually solves this problem that we have of having too fine grain domains. What do we do about it? Which is okay, the different modeling. The second paper. So what they did in this paper was they trained. If you have a data, if you're training a data and now you're testing it on something outside of this data or on a minority subset of this data, when you use MLE, it doesn't perform that well, because MLE looks at what is the average or the most likely thing to happen, and it doesn't look at the edge cases. So the perplexity says is very high for the edge cases. So over here, what they did is Yelp and news, 10% Yelp and 90% news in the training data, and then they tested it just on Yelp data. So they saw that the perplexity was really high. So what we're trying to do is train a model which is able to perform. So we are trying to minimize the worst case testing case as well. So how we do that is next. So okay, this is what MLE does, because we are trying to, so as I just said earlier, it doesn't look at the edge cases, it's trying to look at the average, so it looks at what is the most common one. So over here it will look at news. So then for this, the approach that we have is topic CVAR, where the two main things that are changing are we have topic based sets, and we are also using baseline loss function instead of the ideal loss function. Okay, and this saw 5.5 perplexity reduction as compared to MLE. This is the, now just backtracking a bit, talking about what DRO and CVAC is. So DRO, we are trying to optimize performance, right? But it, this is just, that is the basic thing that DRO is trying to do. Now it has different ways of doing it. One of them was, next slide, CVAR. So how you see in finance, it's similar to what we try to, so it's borrowed from finance, where we are trying to find the risk in the worst case scenario. So you look at only those worst case scenarios, either 5% of the whole thing or something like that. So you are over here in CV. No. Worst case would be when the testing data is part of, like, either it is similar to the one of the domains, so then it's not something which was there in the training set, so that is the worst case, or when it is of the minority domain, or it is, so if it's 10%, 90%, and you switch the percentages. So in this case, they just took that because they already decided how the data is going to be trained. They took the worst case as it just being all Yelp reviews. The testing training data was Yelp and news, higher news. We can, like, they change the numbers around. And then they tested on Yelp, and they also tested on TripAdvisor, which is similar to Yelp, but it's on trips. So it has a so over here the subpopulation shift thing is there. When we're testing the data, it has to have some similarity, but need not be completely what is there in the data. Okay, so over here, what we do is we look at those sets which are part of the worst part. So the minimum, so over here alpha comes in, which we are designing another set PX alpha, which is the minority set, or which is the one which is not performing that well in the whole domain, and we optimize those weights, or we change those weights around. This is known as sentence VAR, sentence CVAR, because over here they're looking at each sentence individually and then they're finding the sets. But the limitations over here is overly conservative. There are some sentences which we don't want to use at all because they were either too noisy, they might be grammatically incorrect, but they would have they would have a really high loss. So now when you use CVAR, it would increase their weights as well, which would lead to um, worse performance than usual. Then the log loss bias issue. Um, there are some sentences which are inherently tough to train, no matter what. So they are high entropy cases. For those, the log loss would be low, would be very high, but no matter how many weights we give, how high weights we give them, they wouldn't be able to learn. So because of that, we end up wasting our um, computational energy on those sets, and overall the set doesn't perform as well. So for this is where topic CVR came in, which has two solutions, which is a topic based approach. Instead of just using sentences, they bunch each of them into domains. So this is the thing they do over here is they use machine learning, they use light LDA for this to train 2023 or 2019. 2019. Huh. The other one was 20. Huh. The other one is 2023, but that also didn't use this. Huh. So that's why we weren't thinking of using LDA because we already have the topics defined in the data set we have from Pi. We already have the domains. So this is just what they've done, but it's not something we're thinking of using. So there now the data sets that we take, the alpha depends is now used on the domain, not on each sentence specifically. And now we're trying to minimize that loss of each of those topics. Next. So this is where now the high entropy problem that we have, that is where we use baseline loss function. This is we find the KL divergence between what we are getting right now and what the optimal one is. So what ideal case it will behave. Now we don't have the ideal case information. So we use it. So for this, they don't exactly tell how they find the ideal case, but they say that based on how it had been performing and you tested on previous things, you try to find the ideal loss and how it was performing on the reference one. Based on that, you find the loss function each time. Next. So this was just an example of how it's done. Over here, if this is our training data, in MLE, you just look at the ones which have higher average, which is over here. Sentence CVR just gives all of them almost equal weightage based on how tough they are. Now, when you just use log loss, that time the ones which have high loss, so this is, for example, these have high entropy, these are still given higher weightage. But over here, we have changed the complete thing because this is the toughest to learn, the B1, which was the review, while the news were easier than that. So that is, they now change the weights. Next. So the benefits of this are we are also able to see which model or which specific topic in the model is struggling the most, and it doesn't matter if a few of those sentences aren't correct over here, and then we are optimizing it better as well. Next. So it's done in 3 steps: the LDA topic identification, then the baseline estimation, and then they use an online optimization to get the final weights, which is because it's a min-max game that's being played now. It's not just a simple minimizing thing. So where they'll alternatively, in the online optimization, they alternately run between the two, minimizing and maximizing, and keep iterating it each time. And then this is the experimental setup. So the data says that they had a Yelp review, 1 billion world benchmark, which were the news information, and TripAdvisor hotel reviews. And then, yeah, okay. So, yeah. So over here now, what we saw how the data was performing. If you use MLE, the perplexity was high. So it topics. Okay, another thing. Alpha, so which is alpha was what we're taking as our optimization thing, the set. And alpha star, because we have only 2 reviews, alpha star is the fraction of Yelp reviews in that. So topic CVR will perform the best when alpha is equal to alpha star. because then it'll take that only as a subsection. So they have taken the assumption that they know what alpha is and an alpha star is, and based on that they've computed it. Now, when we do early stopping in MLE, that also helps because it helps prevent overfitting. So they've looked into that, and Oracle is when we exactly know what we're trying to uh, what we're trying to test. So the topics in Oracle, the topics aren't decided based on training; they are already given. So this is what we would be doing. Yeah, is what similar to what we are thinking of. Huh.
Which are the parameters that we should be less than I mean, for example, here also.
Huh. Yeah, what we were thinking was combining both because Doremi is training it, right? Because in the end, the training, this is part about training, and that is how we are like increasing it to a higher data set. So we were thinking over there the baseline log loss and the way topics are being used. So the one we are defining, the predefined topics that we are using. No, it's not. Huh. Domains which are the information coming from, which is from where the information is coming. So they just have Wikipedia, or there was no notion of topics. In our domains, the ones we have. Topics are. So the data we have right now, the pile data set, that has the domains. That, so for that we have the topics. Yeah, but then we can teach it using light LDA also then if needed. We were thinking of looking into that also. We didn't know how that works. They told us not to focus on that too much. Otherwise, we were going to look into how the topics were formed. Yeah. Yes. Yes, yes. Baseline Doremi, just the weights being trained, and the weights that have been defined would be done using topic CVR instead of group LD. Huh. Yeah, okay. Then this was end end. पीछे नहीं सामने है खत्म करना beyond. Okay, these are just results that we got on how it's performing if alpha isn't too close to alpha star, if we don't have baseline and all, which is then we also saw that this is the same assumption that we had. MLE performs well on those data which is easy. So over here, MLE performs better in those which talks about the news, accidents. Over here, we get more about the serving and stuff because that is what was there on Yelp. And news may we would get about accidents, locations. MLE is doing better there. Next. So the conclusions we got, and next, the project we were thinking of doing. So our biggest limitation is both of these papers use FairSex when they're doing the code, and they have code for both, but we over here use Nemo. So it will replicate anything, we would have to change the complete architecture behind it.
But I thought Shravan and Dima, I mean, they'll help you very
Yeah, they said we have to use Nemo.
Yeah, because that's when we can run the experiment at scale. Otherwise, FairSeq will not be able to. Yeah. But they already have a lot of things in place. In fact, Bhagwan has already implemented data mixing.
We don't know.
Bhagwan, today morning I had a call with him. He has already implemented it. You won't have such a hard problem. He's already implemented it.
Okay. So we were thinking, he told us he would give us.
He was trying to do this. So someone else is implementing, not he, but someone else implementing.
So what they told us, they would give us the data set, the pile one, and then train it for.
Shravan has implemented, I think.
No, he hasn't. But
okay, just talk to them.
And they.
The meetings you do this experiment on bird too. Bird. I could do this experiment on. If you want to look at a pile, pile can be of that order, right?
Pile had 2 billion parameters stuff, so that's why we train it on smaller ones, like do 250, 300, 350 and see how we can scale it up to 8 billion, 2 billion in that. So we're thinking we will try doing that, see how topic CVR is helping when we're changing the domain weights. Are we taking lesser time because the weights are getting optimized faster?
Topics certainly give you interpretability, but even if you go back to Doremi, yes, anyways, you have done with this slide, right? Doremi, I feel
Which part?
Yeah. This is good enough.
Acha. To be.
So instead of trying to have topics as a separate thing,
We were saying
somehow,
this step only we would use topic CVR in the
yeah, I mean,
training.
okay, that's what you're
Yeah.
thinking, right? Yeah. So, I mean, stick to Doremi as a
Yeah,
framework.
Doremi is the main thing. When we're training it, we think that if we use topic CVR, it would converge faster and the number of steps you would need would also reduce. So we would also do the extrapolation and use topic CVR. We're thinking we'll
But
try
you need a
both.
reference. You need a
Reference model.
right?
Yeah, that we have to talk with them how that
And the
happens.
reference model should be
Have the
have
same
those
topics. Huh.
So without those topics, how is the reference model?
So that we'll have to figure from them
So
how.
I feel don't force topics. There's enough to be done even with Doremi, I feel.
Okay.
Anyways, baseline is a must. So
Uh-huh.
just get the baseline done.
Yes.
And then one possibility is that, I mean, what if you use domains as topics? I'm just
That is
thinking.
what they've done here. Their domains are what they've used here. So we were, and
But they have not, I'm saying, they have not really used the BRO
properly.
distribution robust. There's no robustness.
Yeah, that's not there. But then we know that if we have topics, it would do because in a certain domain, then you would have different topics. You could have news, we could have weather in the same domain. If we make it into topics, we are actually optimizing its operations as well.
Okay. Why don't you discuss further with him? Good idea. So you guys changed this
On
you
Monday.
accepted this topic.
Yeah.
You read this in how many days?
5 days.
And how many other what did other papers you had?
Other, we had 3 on tokenization.
So you presented only one.
Only one. So at that time, actually, we both had some personal things going on in our life, so we weren't able to focus too much on this. So we are told that's why our presentation had got pushed forward also that time.
Okay, so you voluntarily accepted that you
Yeah.
You're excited about it.
Yeah.
I want to put that on record.
Yes,
That,
yes.
and you had not prepared earlier,
Yeah.
which is fine. But I think you have ramped up quickly. So fine. Don't blame Prateek.
We took it.
I know you're taking it the right spirit, but so good. I think this will be a very interesting project.
presented to Fundeshwar and tomorrow, and then
Please, good. I think very good outcomes can be sought from this. It will be very impactful.